Hello. In this presentation, we will introduce approaches to contaminant and degradation analysis with FTIR. FTIR is useful for contaminant analysis and degradation analysis. It is characterized by quick, non-destructive qualitative analysis. For FTIR, no chemical pretreatment is required. The measurement is completed in a short time frame, from 10 seconds to a few minutes. In general, qualitative analysis using spectra requires specialized knowledge, but analysis is aided by libraries with many spectra stored in them. Both organic substances and some inorganic substances can be measured using FTIR. Let's take a look at the workflow of contaminant analysis in FTIR. If you find an abnormal part in a sample, first collect it and observe it with a stereo microscope. Check the condition and the shape of the contaminant. Then determine the appropriate instrument and methods for analysis. This slide introduces effective tools for checking the condition of contaminants and collecting them for the FTIR measurement. With a stereo microscope or magnifying glass, it is possible to check the measurement points in more detail and to select the microsamples. A sampling kit, including tools such as tweezers or a microknife that is convenient for scraping, can help you to handle very small objects. As we will explain in detail later, a microtome is particularly useful for getting a smooth cross-section. This section describes how to use FTIR to analyze samples. FTIR stands for Fourier Transform Infrared Spectrophotometry. When the sample is irradiated with infrared light, the sample absorbs the same amount of energy as the vibration energy. The vibration energy of each functional group is different, so the structure of the contaminant can be estimated by the position of the peak wave number in the IR spectrum. Next, we need to select an instrument according to the size of the sample. If the sample size is 100 micrometers or larger, then single reflection ATR spectroscopy is suitable. Infrared microscopy is used when the sample size is between 10 and 100 micrometers. ATR spectroscopy makes qualitative analysis easier. ATR stands for attenuated total reflection. Total internal reflection occurs when angled infrared light travels from a high to a low refractive index material. In this case, the prism has a high refractive index and the sample has a low refractive index. However, the light penetrates less than 5 micrometers into the sample. When the light is reflected in this way, some absorption occurs. By measuring the reflected light beam, we can derive an infrared spectrum. This is because the wavelength is proportional to the penetration depth in the sample, as shown in the formula. In other words, from left to right in the infrared spectrum, the penetration depth increases. With ATR spectroscopy, it's possible to measure solids, liquids, and powders without any pretreatment. This makes it simple to analyze samples qualitatively. Here is an example of the workflow for qualitative analysis with FTIR. First, we need to set the scan parameters, such as the measurement mode and the number of scans. Next, we perform a background scan with nothing on the prism. The energy spectrum shown on the right is obtained. After the background scan is complete, the sample is placed on the ATR prism and compressed by the sample clamp. Now we can perform the sample scan. The infrared spectrum shown on the right is obtained. Then we perform a search for the obtained spectrum in the selected libraries. The libraries are categorized into measurement methods or else by sample type such as organic substances or food additives. It's important to select the appropriate libraries in this step. After the spectrum is searched, matching spectra are displayed in order of similarity. Check for the best results by referring to the numerical scores and the peak shapes. Although we have just described ATR spectroscopy as requiring no pretreatment, in fact the accuracy of qualitative analysis can be improved with a small amount of pretreatment. For ATR measurements, close, even contact with the prism is an important factor in obtaining a good spectrum. Hard or uneven objects have poor prism contact, and it is difficult to obtain a good spectrum. Here are 3 ways to improve prism contact. If the substance is powdery, grinding it more finely will increase the contact area. In this case, grind with an agate mortar, etc., as used for making KBR pellets. When there is no flat surface to measure, flattening with a hand press can be effective. This is also a hand press used to make KBR pellets. Pressing a sample in this way makes it thinner, increasing the contact area. It may also be possible to obtain a smooth cross-section by cutting the sample. Smooth cross-section allows more contact with the prism. 2 spectra are shown here, before and after flattening. Compared to the spectrum before flattening in black, the spectrum in red demonstrates that the contact between the sample and prism was improved by flattening the sample. You can see that the contact area with the prism has increased, and with it the intensity of the spectrum. If the intensity of the spectrum is high, small peaks can be observed, and the influence of noise is relatively small, so the overall accuracy of qualitative analysis is improved. There are cases where we want to measure contaminants on the surface of the sample. For a typical ATR attachment, the measurement surface is placed facing downwards, and the position is checked by eye. However, it is difficult to see whether the contaminant or discoloration to be measured is in the correct position, because only the reverse side of the sample can be seen. The operator can get around this problem by taking several different spectra with the sample in different positions. However, there is no guarantee that a measurement will be taken in an optimum position. There are ATR attachments that can solve this problem of sample positioning. The Gladiator Vision and Micrometer Vision, shown here, can show the area being measured in real time. The camera on the measuring surface side transmits an image to a monitor on the ATR device or on a PC. It's easy to adjust the sample position to measure contaminants on the surface and discolored areas directly. These graphs show the results of measuring the contaminant on the filter paper. On the left, the spectrum of the discolored area of the filter paper is compared to the spectrum of clean filter paper. The arrows indicate differences. These peaks are not present in the normal filter paper spectrum. By searching in the library, we can find a match for the spectrum, as shown on the right. The contaminant was identified as sucrose. Now we look at the case of mixed contaminants. In real-life analyses, there will normally be more than one component. The slide shows an example of searching the standard library for food contaminants in a sample. The sample spectrum, shown in red, almost matches the spectrum for starch. However, due to the presence of lipids and other substances, it's different from the search result. The split peak near 2,900 is large, and there is a sharp peak at 1,720. Because the spectrum includes additives as well as the main component, it is important to obtain a large amount of spectral data from the sample for more accurate qualitative analysis. There may also be spectral changes due to degradation. This example shows acrylonitrile butadiene, or ABS, processed in an oven at 300 degrees for 2 hours. There are various reasons for degradation, but when plastics are degraded, they crack and lose flexibility, so inevitably they get mixed in as contaminants. The spectrum of a degraded product is different from the spectrum of the standard product. The peaks of OH and CO double bonds due to oxidation are particularly noticeable in the case of heat degradation, so searching the standard library will not result in the best match. Shimadzu has released the plastic analysis system Plastic Analyzer to assist in plastic analysis, including degraded plastics. The Plastic Analyzer consists of the Fourier transform infrared spectrophotometer IR Spirit, QATR-S as an attachment for single reflection ATR, and a method package. The UV damaged plastic library and the thermal damaged plastic library allow accurate analysis of degraded products, and the method package supports IR pilot measurements. This enables a simple FTIR workflow, which can be carried out even by inexperienced users. Plastic Analyzer has three key features: highly accurate degradation libraries, simple measurement using an analysis program, and a small footprint. Spectra obtained by stepwise ultraviolet or thermal degradation of multiple types of plastics are recorded in these libraries, enabling highly accurate spectrum retrieval and qualitative analysis which reflects the degradation state. In addition, simple measurement using IR Pilot allows even users unfamiliar with FTIR to perform measurements and spectrum searches without having to input detailed conditions. Finally, with the compact FTIR IR Spirit and the ATR integrated into the sample chamber, the footprint of the instrument is the size of an A3 piece of paper. As an example of degradation analysis, we analyzed a fragment of a traffic cone that had been degraded by being left outside. This is also a demonstration of analysis with the plastic analyzer. First, we click Plastic Analysis in IR Pilot. A wizard will appear to take us through the background scan. The background scan begins using the default scan parameters and is completed in about 1 minute. Next, the sample scan wizard appears. Set the sample and click OK to measure the sample spectrum. This also takes about 1 minute. Once the sample spectrum has been measured, the program will automatically perform a spectrum search and report the output. This graph shows the spectrum of the fragment of traffic cone and the spectrum from the UV damaged plastic library of ethylene vinyl acetate. EVA is a material used for softer cones. A good match was obtained with EVA that was irradiated with 150 megawatts per centimeter squared of ultraviolet light for 450 hours using an ultra-accelerated weathering tester. In both spectra, we observed a broad peak of OH at about 3,300, which is not seen in the reference standard, and broad absorption over the lower wave number region. This is an example analysis of a vehicle headlight. It's important that the plastic of these headlights be transparent, but it may turn yellow with use over time. This discoloring is also assumed to be caused by UV light. In addition to the plastic analyzer mentioned before, these plastics can be measured with various different analysis methods and sampling methods. We refer to the part with noticeable discoloring as the discolored part, and the part which is relatively colorless and transparent as the normal part. For the normal part, we measure sample 1, the section obtained by cutting with a microtome, and sample 2 from the surface. To obtain a surface sample of the discolored part, we scrape off small pieces with a knife. In this case, the front surface was designated as sample 3 and the reverse as sample 4. First, let's look at the analysis results for the normal inner material. Since this part is not from the surface, we can find out the base material of the headlight. Standard polycarbonate was a very close match. The spectra overlap on this graph, so they are difficult to distinguish by eye. This is the analysis result for the normal surface sample. We searched for the spectrum and found matches with UV irradiated polycarbonate and polymethyl methacrylate. The large peak near 1680 is not found in polycarbonate, so we assume that sample 2 is a mixture of these two spectra. PMMA is a component in coating agents which prevents damage from ultraviolet light and scratches. Polycarbonate was a match for both sample 3 and 4 from the discolored part of the headlight. The coating agent on the surface that we saw for the normal part is not seen, and we assume it has been worn off. The spectrum of sample 3, shown in red, is compared with the spectrum in black of polycarbonate UV irradiated for 550 hours The absorption of the OH stretching vibration at 3300 was similar. That is, the degree of degradation is comparable to that of polycarbonate irradiated for 550 hours in an ultra-accelerated weathering tester. However, when we measured the reverse side of the discolored part, we found that there was almost no deterioration. Only the surface is degraded, even for the discolored part. This is a summary of the analysis results for the vehicle headlight. From the analysis results of the normal part, which was not noticeably discolored, we found that the base material was polycarbonate. In addition, a coating agent containing PMMA was detected on the surface. On the other hand, no peak from this coating agent was observed on the surface of the discolored part. The degree of deterioration was about the same as that for plastic exposed to ultraviolet light for 550 hours in the ultra-accelerated weathering tester. This degradation was limited to the surface. In summary, ATR spectroscopy, which does not require pretreatment, is suitable for contaminant analysis. In the case of hard sample measurements, it's useful to improve contact with the prism, for example by flattening the sample. There are ATR attachments which are useful for checking the sample position in contaminant analysis. The analysis program in the plastic analyzer makes qualitative analysis with FTIR easy and smooth. Shimadzu's unique libraries, such as the UV damaged plastics library and the thermal damaged plastics library, improve the accuracy of qualitative analysis. Thank you for listening.
Excellence in science. Shimazu.